In today's video, we are going to talk about the volume of a different kind of solid object, one that's not made by revolution. So we'll see how this one looks. Let R be the region bounded by the graphs of y equals e to the x. We know what exponential growth looks like. And the line y equals 3. And the x-axis. So the region that's surrounded by all three of those, that's this area in here, is the base of a solid object. The cross sections of that solid object are going to be rectangles. And I'm actually going to change the question just a tiny little bit. Instead of 4 times, I'm going to make that 1/4, only because it'll make it easier to draw. Okay. So what we're going to do is make a solid object by making cross sections that are rectangles sticking up out of this base. If you imagine an infinite number of rectangles, short rectangles, the height is only 1/4 as big as the width. So when the width here is that distance, so that's my first, call that the width of the rectangle. My first measurement there is the distance between the line y equals 3 and the line y equals e to the x. And that, obviously that'll be different here and here. Each one of these spots will have a different width. In each one of these spots, the height of the rectangle will be 1/4 as big as that width. So let me change color here. So the height of the rectangle will be 1/4 as big as the width, and so we'll make a rectangle out of that. Because this width is bigger, the height of the rectangle will also be bigger here, and it'll be bigger still here. And if you can imagine, it'll be at its biggest here. If you can imagine the edge of the object we start here, it'll sort of make, it'll follow along the corners of the object. So we've got a solid figure built out of that. And hopefully you can tell that the different colors represent different dimensions right now. Okay, so the height of that rectangle, which I drew in red, I accidentally drew too much in red. This should be in blue, because this is the same. These lengths are the same as the width. But the height in red of my rectangle, the problem tells me, is 1/4 as big as the width. So I'll write that as 3 minus e to the x over 4. Sorry, just to be more consistent, I call it the width. I really should have called it the length, only because that's what the problem called it. Okay, so that is our one-dimensional measurements. The two-dimensional measurements would be if I want to find the area of that cross-section. So what I'm going to do is imagine finding the area of this cross-section right here. Well, that cross-section is a rectangle, so its area should not be that hard to find. It's just the length times the width, which I call the height here. So it's the length times the height, which is the same thing, over 4. So 3 minus e to the x squared over 4. And as we've seen in other examples, what we're going to do now is give that, in order to get to the 3-dimensional volume of that slice, we're going to give it a little bit of thickness. So I'm going to make each object a little bit thicker. So now it's a solid little slab or a slice, and that volume of the slice, which we of course know is called dV from last class, is just the area of the base. Sorry, that should be an equal sign. The area of the base times the thickness, which, like our examples from the other class, the thickness is just dx. And so now we have the volume of our solid object is 3 minus e to the x squared over 4. And so if I want to add up all of my solid objects, so if I, this one, and I put them all together to find the volume of the entire thing, that would of course be the overall volume, which would be the sum of all of these products. Remember, the dV is a product, the area of the base times the thickness. And if I want to add up all of those different products, we of course know the sum of a bunch of products is the definite integral of the area, the volume of the base, integrated from, and now we just have to think, where do we start integrating? Since our dx is the thickness, that means we need to start from the lowest x value here, and we need to go until the last x value here, which we need to figure out, where do these two lines equal each other? Where does e to the x equal 3? Well, it's not a very pretty number, but to solve for x there, we would take the natural log of both sides. So x is equal to the natural log of 3, and that is where I would integrate into. To do this integration by hand, we would actually need some tricks that we don't know yet. We won't be learning for quite a while because we've got a exponential inside of a quadratic, and we don't have any tools for that yet. So we'll leave it like this and say that that is the volume. If you wanted to plug it into a calculator, you could do it that way.